For centuries, humanity has gazed up at the night sky, captivated by the twinkling lights and the profound mystery of the universe. Every star, every glimmer, is a tiny beacon in an expanse so vast it defies imagination. Yet, for all we have learned, the cosmos still holds secrets, entire structures hidden from our view. We've explored much, but what if some of the most fundamental components of our universe have been silently, patiently, waiting to be found? What if there are entire cosmic cities we haven't even begun to map? Before we delve into the hidden, let's establish a common understanding. What exactly is a galaxy? At its core, a galaxy is a colossal collection of stars, gas, dust, and dark matter, all bound together by gravity. Our own solar system resides within the Milky Way, a majestic spiral galaxy spanning over 100,000 light-years. Galaxies come in various shapes and sizes, spirals, ellipticals, and irregulars, each a cosmic island containing billions, even trillions, of stars. They are the fundamental building blocks of the large-scale universe. For most of astronomical history, our understanding of the universe has been shaped by visible light. Optical telescopes, whether on Earth or in space, capture the photons, tiny packets of light, emitted by stars and nebulae. This method has allowed us to chart billions of galaxies, mapping the cosmic web and observing phenomena across incredible distances. We've seen grand spirals, faint dwarf galaxies, and massive galactic clusters, building an awe-inspiring picture of the cosmos. But what if this reliance on light creates a fundamental blind spot? Imagine trying to find a city in the middle of a vast desert, but the city itself emits no light, has no tall structures, and is shrouded in a perpetual fog. This analogy helps us understand the challenge of detecting a hidden galaxy. These aren't necessarily dark, empty voids, but rather galaxies that are incredibly dim in visible light, or perhaps obscured by cosmic dust, or even too far away for their faint starlight to reach us effectively. They exist, but they remain elusive, mere gravitational whispers in the cosmic background. This is where the enigmatic dark matter comes into play. Dark matter is a mysterious substance that does not interact with light or other forms of electromagnetic radiation, meaning we cannot directly see it. However, we know it exists because of its powerful gravitational influence on visible matter, stars and galaxies. Scientists estimate that dark matter makes up about 27% of the universe, dwarfing the ordinary matter we can see. It acts as an invisible scaffold, holding galaxies together and influencing their formation and movement. If visible light isn't enough, how do we search for these shadowy structures? The answer lies in turning our ears to the universe. Radio astronomy allows us to detect electromagnetic radiation at much longer wavelengths than visible light. This is crucial because many celestial objects, especially those poor in stars or obscured by dust, emit strongly in radio waves. Think of it like tuning into a different radio station. The signals are there, just not on the frequency our eyes perceive. This realm offers a unique window into the universe's hidden corners. One of the most powerful tools in radio astronomy for detecting hidden galaxies is neutral hydrogen, specifically its characteristic emission at a wavelength of 21 centimeters. Neutral hydrogen is the most abundant element in the universe, and it exists in vast clouds throughout intergalactic space. These clouds are the raw material for star formation, and crucially, they are often found in the outer reaches of galaxies, even those that appear dim in visible light. Detecting this 21-centimeter signal allows us to map the distribution of gas, hinting at the presence of a galaxy even without bright stars. The ability to detect these faint radio signals has been a journey of relentless technological advancement. Early radio telescopes were rudimentary, but over decades, instruments like the Arecibo Observatory and the Very Large Array have pushed the boundaries. More recently, arrays such as the Square Kilometre Array Pathfinder, or ESCAP, in Australia, are revolutionizing the field. These massive networks of dishes work in concert, creating a synthetic aperture that offers unprecedented sensitivity and resolution, allowing astronomers to peer deeper into the radio universe than ever before. One of the primary goals of these advanced radio telescopes is to conduct deep sky surveys, essentially cosmic censuses. By systematically scanning large portions of the sky, they collect vast amounts of data, searching for the subtle signatures of neutral hydrogen. The challenge is immense, akin to finding a needle in a haystack, or rather, countless faint needles in an unimaginably large cosmic haystack, all while filtering out terrestrial interference and noise. This painstaking work requires powerful computers and sophisticated algorithms to process and interpret the incoming signals. It was during one such survey, using the cutting-edge capabilities of a next-generation radio telescope, that astronomers started noticing something peculiar. A faint, diffuse, yet distinct 21-centimeter signal emanated from a region of space that appeared largely empty in visible light. This wasn't a powerful, obvious beacon, but a subtle whisper, indicating a significant concentration of neutral hydrogen, far more than one would expect from mere intergalactic gas. It was a tantalizing hint, a ghost in the machine of the cosmic data. Such a discovery is never immediate, it requires meticulous verification. The initial signal spurred a flurry of follow-up observations using multiple instruments, both radio and optical, aimed at the same celestial coordinates. The goal was to confirm the signal's authenticity, rule out any instrumental error, and search for any corresponding visible light. While optical telescopes confirmed the region was indeed sparse in bright stars, the radio observations consistently showed the hydrogen signal, reinforcing the idea that a substantial, yet optically faint, object was present. And so, after years of painstaking work, the existence of a new, previously undetected galaxy was confirmed. Provisionally named the Quiet Dawn by its discoverers, this celestial entity stands as a testament to the universe's hidden depths. It's not a grand, active star-forming galaxy like the Milky Way, but rather a diffuse, dark matter-rich system, where star formation proceeds at an incredibly slow pace, or perhaps has almost entirely ceased. Its discovery marks a paradigm shift in how we understand galaxy demographics. The name Quiet Dawn perfectly encapsulates its characteristics. This galaxy isn't a bustling city of bright, newly formed stars. Instead, it seems to be in a very quiescent, or quiet, state. Its star formation rate is exceptionally low, meaning it's not actively churning out new stars like younger, more vibrant galaxies. It appears to be an older, more mature system, perhaps having used up much of its gas supply, or simply never having accumulated enough to ignite a brilliant stellar birth rate. It offers a glimpse into galaxies that evolve differently. One of the most striking features of the Quiet Dawn is its extreme dominance of dark matter. While all galaxies are thought to reside within a dark matter halo, this hidden galaxy appears to be almost entirely composed of it, with very little ordinary, visible matter. This makes it an ideal laboratory for studying dark matter directly through its gravitational effects on the sparse neutral hydrogen and few stars it contains. It might even represent a class of dark galaxies, structures where dark matter significantly outweighs luminous matter to an unprecedented degree. The discovery of the Quiet Dawn compels us to reconsider our models of galaxy formation and evolution. For decades, our theories were largely based on observations of optically bright galaxies. But what if a significant fraction of galaxies throughout the universe are dark matter-dominated and extremely faint in visible light? This hidden population could drastically change our census of galaxies, and thus our understanding of how cosmic structures formed and grew from the early universe to the present day. It's like finding a whole new branch on the cosmic family tree. The implications for our cosmic inventory are profound. If the Quiet Dawn is not an anomaly, but rather an example of a common galaxy type we've simply been unable to detect, then the true number of galaxies in the universe could be significantly higher than current estimates. These dark galaxies might be much more numerous than visible ones, influencing the gravitational landscape and the overall distribution of matter in ways we're only beginning to comprehend. This single discovery opens the door to a potentially vast, unseen universe. Perhaps the most intriguing aspect is that the quiet dawn is relatively close, astronomically speaking. Not in our immediate backyard, but within the larger cosmic neighborhood accessible to modern telescopes. Its proximity makes it an even more valuable object of study. If such a galaxy can exist relatively nearby, what other hidden structures might be lurking just beyond our current observational limits, even within our own local group of galaxies? This discovery urges us to re-examine what we thought we knew about our galactic surroundings. The discovery of the quiet dawn is just the beginning. It highlights the critical need for continued investment in next-generation radio telescopes and advanced data processing techniques. Future instruments, with even greater sensitivity and resolution, will undoubtedly uncover more such hidden galaxies, potentially revealing an entirely new census of cosmic structures. This frontier isn't just about finding more objects, it's about fundamentally changing our perception of the universe, uncovering its true composition and the diverse ways in which galaxies can form and evolve. From the first glimmer of starlight to the faint whispers of neutral hydrogen, our journey through the cosmos is one of continuous revelation. The quiet dawn reminds us that the universe is far richer and more complex than our current observations reveal. It challenges us to look beyond the obvious, to listen to the subtle signals, and to imagine structures we haven't yet seen. As technology advances and human ingenuity persists, we stand at the threshold of a new era of discovery, ready to unveil more of the universe's quiet, hidden wonders.